Hi, this is Team Space Spinners, and this is our presentation on our modified small terrestrial closed washer for long-duration space missions. I'm Lila Bernhardt.
I'm Lionel Pramel.
I'm Ariel Sweet.
And I'm Ashley Yang.
On current ISS missions, each crew member wears about 0.2 kilograms of clothes per day, which is made up of the normal clothes that last several weeks before disposal, but also workout clothes used in their daily exercise, which need to be thrown out every 2 to 3 days once they become dirty and start to smell. This is an unsustainable practice for long-duration missions, and NASA studies have shown that bringing a washing machine system with all of the required water and detergent is more practical and has a smaller equivalent system mass than bringing the disposable clothes. Because of all this, NASA has been designing zero-G washing machines since the 70s that have posed solutions to the major problems facing microgravity laundry. But since the 70s, terrestrial washers have also had several technological advancements and can now be very compact and energy efficient. The scope of our project is to identify a compact washing machine to modify and to run tests on to determine the feasibility of using a terrestrial washer in space.
Given our project background, we developed the problem statement listed here to summarize the mission of our project. TSGC also provided us with a short list of design goals for the machine. For one load, the washing machine needs to be able to clean up to 3 kilograms of clothing, use less than 30 kilograms of water, consume less than 750 watts of power, and have a total mass less than 60 kilograms. So the best way to meet the goals was to start with a machine that already came close to our desired results. We researched several different types of compact washers and selected the machine that best matched our needs and we were able to obtain in a reasonable time frame. As you can see from this table, the machine initially met the target washer mass, power usage, and load size. However, the water usage was slightly higher than our target value. In modification and optimization processes, we strive to reduce the water usage and keep the washer mass and power usage below these thresholds. Once the machine arrived, we were able to begin experimentation to confirm the provided machine properties and to test different optimization methods. In order to run multiple comparable experiments, we used very similar sets of one cotton t-shirt and one pair of polyester dry fit shorts as our control load.
The first set of experiments we conducted at the suggestion of our project mentor was focused on removing as much water as possible from the wet clothes after washing. Doing so would reduce the amount of time and energy required of our sister team working on a terrestrial-based clothes dryer for similar applications to our project. To do this, our group first brainstormed a few ideas for mechanically removing water from the clothes. These ideas included inflating an airbag within the washing chamber to press the clothes against the side of the drum, pressing the clothes against the bottom of the drum using a plate and weights to simulate a linear actuator, and adding masses into the drum to agitate the clothes during the spin cycle. Although not especially feasible because of the added time it would demand of the astronauts, as well as the risk of flinging water that it would introduce, our group also tried wringing the clothes by hand to create an additional point of reference. In each experiment, the weight of the clothes was measured before the wash, before the spin cycle, after the spin cycle, and after the secondary drying mechanism. Each configuration was tested twice to generate a more complete data set, and throughout the experiments, the peak power draw, total energy usage, and water consumption were also cataloged. The results of the experiments showed a consistent pattern wherein the clothes absorbed about 3 times their dry weight in water before the spin cycle, and this spin cycle then removed water until the clothes were 1.6 times their dry weight. None of our secondary mechanisms proved noteworthy. The effectiveness of the spin cycle prompted us to investigate it more closely. By setting up a bucket and recording the mass of water extracted during the spin cycle against time, our group was able to arrive at some meaningful conclusions. In 2 different experiments, one run with the same clothing set as the previous experiments, and the other with the washer filled to its capacity with 3 kilograms of cotton t-shirts, the trend between water and water removed and time was initially linear before falling off at an asymptote just under twice the dry mass of the clothes. It was also observed in both experiments that 90% of this asymptotic value was achieved within 100 seconds and 95% within 2 minutes. From this, we could determine that spinning for longer periods of time would have severely diminishing returns.
To minimize the power consumption of the washer, we measured the peak power draw and energy consumption of our control load of clothes using a power meter. We ran several tests with customizable washing parameters, mainly focusing on the 5 different wash modes: heavy, gentle, soak, normal, and rapid. We applied peanut butter to dirty the clothes, and this helped demonstrate to us that some of the washing cycles were ineffective on their lowest settings, such as gentle and heavy, since they left heavy peanut butter smells and stains. Overall time of wash was positively correlated with energy consumption. We also learned that peak power for all wash modes was within the same 200 to 300 watt range, all during the ramp up to the spin cycle. The circled data points are of the rapid cycle, which both cleaned the clothes effectively and also consumed generally less power. After we finished our experimentation, we moved on to the second phase of assessing the washing machine. We started the deconstruction of the washing machine by removing easily accessible screws and then working inside out. The circuitry throughout the machine tied together several subsystems from the top and bottom, and we were able to remove it by unclipping or unscrewing circuitry at their connection points. We reached a blockage point where the tub system would not come apart through the removal of screws. Therefore, we decided to brute force cut through the plastic of the outer tub using saws, pliers, and bolt cutters, as you can see in the bottom left photo. Throughout the process of disassembling the entire washing machine, we were also categorizing the pieces by weight, material, and additional comments, such as electrical specs or part interaction. A large majority of the plastic parts are injection molded, and most of the metal components are bent stainless steel. These materials make sense due to their interaction with water and ease in mass manufacturing. From the categorization of parts of the washing machine, we came to the conclusion that there are some areas of optimization. One of our first changes would be to replace the current plastic and metal construction with lighter materials, such as structurally placed carbon fiber or titanium. This, with a modification to the tub size, would help us conserve energy in the system by reducing the moment of inertia. We also believe that some components can be replaced with higher quality and lighter substitutes, such as the main motor. For the user interface, the team recommends reducing the cycle choice to just one, since it will decrease the amount of time crew members spend with the machine. In addition, modifying the washer for space use, we would first recommend creating a watertight seal for the lid so that water cannot leave the system. And second, we would recommend connecting a vacuum system to help reduce foam generation.
Through our design, experimentation, and analysis processes, our team selected a compact washing machine that had promising specifications of a low mass, volume, and power draw, which would meet our design goals. We were able to confirm each of these metrics through the measurement and experimentation with the machine, and later through the optimization. We began calculating how much we could lower each metric. In this chart, you can see the mass, volume, and power comparisons between the initial design goals and the 3 washer options. As you can see, while the regular washing machine has too large a mass and uses nearly the maximum power draw, the compact washer and the optimized values are significantly smaller than both the design goals and the home washer. The only design goal in which the compact washer fails is the total water usage. On the rapid wash small load preset, the washer uses an average of 33.2 kilograms of water, which is larger than the 30 kilogram goal. Steps and modifications can be made such that as the rinse water being held and reused for later washes, and this solution has been seen in previous NASA washer projects. These modifications, in combination with the lower specs of the compact washer, would meet all the requirements and would be a feasible design for microgravity use. Using the values laid out in the table on the previous slide, my team has started calculating the equivalent system mass for our trade-off analysis. For this, we have 2 more small tasks, which are to finish our disassembling and categorizing of the assembly that is still stuck together, shown on the slide, which will inform the mass optimizations, and characterizing the drive motor to help us inform our power optimization values. Following these last 2 steps, we will be set to complete the equivalent system mass calculations, assumptions, and comparisons for the trade-off analysis. Hopefully, this will show that the optimized washer is the best option for microgravity applications, and that these modifications should be implemented and tested. Lastly, before the Q&A, future steps to continue this project would include computer-aided analysis to provide the maximum mass and volume optimizations, and to combine those results with low-gravity simulations or tests to prove that this concept would work in practice. Thank you very much for listening, and we look forward to answering all of your questions today.